Hi, it's Jack Roski and Ethan Gershgorn here with another installment of Physics Final Project Show. This time, we're coming at you, sans John Stadler, with some exciting plasma physics.
So first of all, what is plasma? Obviously, you've heard of the three states of matter: solid, liquid, and gas. In some classes, like physics and chemistry, we then learn that there is another state of matter, plasma. Plasma is the next step, energy-wise, after gas. We learn that solids are crystalline structures of basically rigid molecules. One step up, we have liquids, where the molecules have enough energy to break free of the intermolecular forces. Now they are somewhat free-flowing. Then we move on to gases, individual molecules bouncing around with fair amounts of energy. Finally, we go to plasma. Plasma is essentially a gas that has been given enough energy that some or all of the electrons surrounding it break free. This happens when the energy is more than the ionization energy of the nucleus. This yields a mixture of delocalized electrons and ions, and because of these delocalized electrons, plasma has an extreme ability to conduct electric current. Plasma is actually more conductive than any metal due to this fact. Plasma actually gets its cool color from when it accepts an unbound electron. The excess energy the electron contained is converted to electromagnetic radiation with a specific wavelength dependent on the atom. As we know, wavelength determines the physical color we see with our eyes.
So, where can plasma occur? Now that we've established what plasma is, we can now begin to delve into where it occurs. Probably the most obvious source of plasma is from stars. Stars are giant balls of mainly hydrogen plasma. However, there are a significant amount of helium, lithium, and carbon in normal stars. The energy to ionize the atoms inside the star come from the kinetic energy they gain from the initial formation of the star, and then is maintained by the energy released from the fusion that takes place inside the star. Also found in space are, space plasmas. Space plasmas consist of things like in the tails of comets and the accretion disks surrounding black holes. The immense kinetic energy atoms gain as they fall into a black hole and bounce into other atoms also falling into the black hole is enough to ionize the atoms to form a plasma. In fact, it is so energetic that the wavelengths of light released are no longer primarily in the visual spectrum, but rather they begin to release X-rays and even gamma rays. A fun form of plasma that most of you have encountered is a plasma ball, or those toys that show filaments of plasma coming out from a center sphere, and they stretch out to the edges of glass and concentrate when you put a finger on the edge of the glass. Finally, plasma also occurs in fusion technologies that humans have created. Although fusion technologies all have the same goal to get a sustained fusion reaction that puts out more energy than it takes in, it is done in a variety of ways. Due to this, plasma is formed in a variety of ways. First, there's an attempt to electrically confine the plasma, called inertial electrostatic confinement, or IEC. IEC uses a negatively electrically charged wire grid. Because of the negative charge on the grid, electrons are stripped off of the atoms because they are so strongly repelled by the electric field created by the grid. The now positive nuclei are accelerated to the center of the electric field where they collide with great kinetic energy to fuse. This is a form of confinement used in the fuser. However, many of the nuclei slam into the grid, making them unviable to fuse, so energy is wasted. In order to remedy this, magnetic confinement was proposed. Magnetic confinement uses electromagnets to create a strong magnetic field to accelerate the atoms, and they ionize in a similar way to the strong electric field previously talked about. They are then accelerated to slam into each other with great kinetic energy and fuse. This is a type of confinement most commonly used today in the tokamak reactors. Recently, there's been an effort to use lasers to ionize and fuse atoms in order to cut down on costs and energy on expensive electromagnets. A high-powered laser is used to impart enough energy to a fuel pellet consisting of deuterium and tritium, the isotopes of hydrogen used in fusion, to strip their electrons and give them the required energy to fuse with one another. These experiments are conducted at places like the National Ignition Facility, or more commonly heard as NIF.
Thanks, Jack. Now we have to ask ourselves, how much of plasma is actual plasma? So now that we know where and why plasma is made, the question is begged as to how much of the plasma is actually ionized gas. This is determined by something called plasma density. What plasma density actually measures is the density of electrons inside the plasma. Electron density is directly related to the percent of the atoms that are ionized, or the degree of ionization. This is, of course, related to the type of gas being ionized, or the energy put into ionizing it. Next, we ask ourselves, how hot is plasma? The entire time, we have been saying that plasma requires loads of energy to be created. A question that may have popped into your heads is, how hot is it? Well, I cannot give you an answer because that depends on the degree of ionization, where plasmas fall into two categories, cold and hot plasma. A cold plasma has a degree of ionization of approximately 1% or lower. When the degree of ionization begins to get higher than that, it is considered hot plasma. In the fusor, at the point of fusion, the average plasma temperature is around 15 million Kelvin, but that is a particularly hot plasma.
Related to the temperature of the plasma is another grouping of plasmas, thermal and non-thermal plasmas. Thermal plasmas are designated as plasmas where the temperature of the ions and the temperature of the electrons are approximately the same. Non-thermal plasmas are designated as plasmas where the ion temperature is different than the electron temperature. Due to electrons being much less massive than the nucleus, the electron temperature is usually much higher than the ion temperature. Sometimes, in non-thermal plasmas, the ion temperature is not that far above room temperature.
Now, we'd like to show you a simple demonstration of a plasma ball. This plasma ball is primarily composed of neon and argon, as well as other noble gases in smaller quantities. When it is turned on, a high voltage is applied to the center dome, which ionizes the gases and creates these filaments of plasma. These filaments are particularly interesting because the magnetic field created by the plasma itself forces the plasma into strands, which circulate around themselves. This yields the cool formation seen here. When one touches the plasma ball, the finger now acts as a coupled capacitor with the inside of the glass and the outside. Charges flow from your body to the outside of the glass, making it more energetically favorable to concentrate the plasma to the spot where your finger is touching.
Well, that pretty much does it for this installment of Physics Final Project Show. Until next time, I'm Jack Roski.
And I'm Ethan Gershgorin.